Guys, hello. So welcome to lecture 3. Normally, of course, I am happy to take questions at the end of lecture. Today is weird because today I have, actually my meeting is supposed to be at 11 o'clock, but I'll be a little late for it, I guess. I will have to leave this building right after today's lecture, and so I won't be available to answer questions. But you all know when my office hours, right? You all know when my office hours are and where my office is? No? Okay, my office hours are Monday and Thursday, BGS 3046. Those are posted on OWL, the specific times. And importantly, you don't need an appointment to come to my office hours. Just show up and I will be there. And I will talk biology with you, and if you have questions about viruses or falsifiability or blobfish or anything, or birds, I will be happy to talk about all that good stuff with you. Even if you just want to come by and listen to other people's questions, that's cool too. Okay, so you don't need an appointment to come to office hours, just show up. Otherwise, I'm sitting there all alone and sad. So please consider yourselves invited to office hours. And next lecture, for you guys, it won't be me here. It's going to be back to Nikki teaching you all about genetics, how mutations happen, where genetic variation comes from. So I won't be back here lecturing you until like after Thanksgiving. But I will still have office hours, so if after today's lecture, for example, you realize that you don't understand something from one of my lectures, please come by. All right, so today is kind of an active class. We're going to be clicking. Hopefully iClicker Cloud is going to work for me today better than it did yesterday. But we're going to be clicking. You will see sort of multiple choice type questions. We'll also do some small group discussion activities because that's how we roll at the end of a lecture cycle around these parts. Today's lecture title, so that's why we had the scare quotes around lecture 3. It's not just a standard lecture where I just stand here and blah, blah, blah for the full 50 minutes. I'll do that some of the time, but not for the entire class, I promise. The title of today's lecture, Why Evolution is True, you can see, is shamelessly borrowed from Jerry Coyne's book of the same name. This is an awesome book that takes the time to go through something that I won't have time to go over in detail today, but what sort of lines of evidence are there for evolution? Why do we believe that this is the correct way to represent how life on Earth has come to be the way it is? It's a great book and strongly recommended to you. Not required reading, obviously, for this course. All right, I want to take the temperature of the room. If I were to put this question to you, humans evolved from earlier species of animals. What do you think about that? What do you think about this statement? Get yourselves onto iClicker Cloud if you can, and if it doesn't kick me out. So if I were to ask you, is this probably true, probably false, or you don't know? Oh my gosh, it's working. That makes me so happy. Keeping in mind that the people in this room are perhaps not a totally random and representative sample of the North American population. All right, I'm going to stop the poll there. Sorry if you didn't get to click in. Okay. 87% of the people that were able to answer that poll agree with this idea that just like HIV has some sort of evolutionary history, just like most life on Earth has some sort of evolutionary history, so do humans. The same is probably true for our own species. Obviously, that is a view that I myself have as well. So close to 90% of the people in this class would agree with that statement. And we can There we go. Now, about 13 years ago, a poll was put to the citizens of 34 developed countries in the world. This is a poll conducted and published in Science magazine, asking basically the same question, or taking the same survey. What do you think about this statement that humans evolved from earlier species, in this case, earlier species of animals? And the proportion of the population of each country, the countries are arranged here in rows, the proportion of people agreeing with that statement, saying, yeah, that's probably true, are shown here in blue. And the proportion of people disagreeing with that statement, saying it's probably false, are shown here in red. And the countries are ranked with the highest acceptance of evolution, human evolution, on the top, and the lowest on the bottom. Now, citizens of Canada, for whatever reason, were not asked for our take. But our neighbors to the south, of course, were. And you may see, if you have super awesome compound fly eyes, you may see where the United States falls out on this poll. It ranks number 33 of the 34 countries surveyed. It had the second lowest proportion of people agreeing that humans probably have an evolutionary history. Second only to Turkey. It was the Scandinavian countries that tended to have the highest acceptance of evolution in the survey done in 2006. So evolutionary theory enjoys sort of a funny status in terms of other scientific theories, in that it is overwhelmingly accepted, bless you, by the scientific population and by people that are, have fairly good scientific educations, like yourself. But there's huge portions of the population, at least in the United States, I would say to a lesser extent in Canada, but still substantial proportions of people do not believe, at least, that our own species has an evolutionary history or is subject to forces like natural selection. Some polls, like the Gallup organization, polled people and did it longitudinally over time, over about 40 years, and they went a little bit finer still. They said, okay, which of these best describes your views about the origin and the evolution of humans? Do you think that God created humans in their present form relatively recently, within the last few thousand years? Or do you think that humans just have an evolutionary history, there's no need to bring God into this? Or do you think something sort of in the middle, that maybe humans are subject to evolution, but that there's some sort of supernatural guidance going on in there too? So giving people a few more choices. And then measuring the attitudes of people, again, in the United States, from about 1982 to the present, to the year 2019. And humans evolving without any input from God is the bottom line on this, the dark green line. And continually the most popular opinion among the people surveyed, ranging from 44 to 46 to 40% of people surveyed in any given year, is this idea of what we can think of as young Earth creationism, that humans were created pretty much in the same form that we have now within the last few thousand years. So that is sort of what we're dealing with in terms of public attitudes towards evolution. There's a little bit of an uptick in the proportion of people accepting human evolution, up to 22% of people surveyed in the last year, which is maybe a little bit cause for cheer. So evolution is, of course, a polarizing idea, much more so, I think, than other scientific theories are now. Most people would ascribe to the germ theory of disease, to gravitational theory, to the idea that the Earth rotates around the sun and not the other way around. So it's about 160 years, exactly 160 years next month, since The Origin of Species, famous book by Charles Darwin, was published. And as you can imagine, it's a polarized, evolutionary theory is a polarizing idea now. It was perhaps even more polarizing at the time. And there were all sorts of little nasty cartoons and stuff in the public press. The defrauded gorilla, that man wants to claim my pedigree. He says he is one of my descendants. And the guy, now Mr. Darwin, how could you insult him so? That was very comical in 1859. Any thoughts as to what it was about evolutionary theory that people didn't like, that rubbed people the wrong way? Yeah.
Evolutionary theory, so technically when Lamarck and Aristotle had this scale for the evolution, they said the God is the perfection, before that is human, and like we don't have any around there.
Yeah, that's a great point. So most thinkings about about life on Earth involves sort of a scale or a hierarchy with humans, specifically white male humans of European descent, probably being at the very top of the hierarchy, and then a whole mess of sort of lower evolutionary forms. And sort of tied to that is the idea that when Darwin proposed that no, everything on Earth is related through common ancestry, everything on Earth is related to everything else, even things like humans are related to things like plants or beetles or bacteria or slime molds, that was considered sort of insulting at the time. And evolution, specifically whether evolution should be taught in publicly funded schools, remained a controversial issue. Here's a shot of two of the lawyers involved in the so-called Scopes monkey trial in 1925. You don't need to know the dates of this trial or the names of the lawyers, but just to present some context, in 1925, the Tennessee legislature passed a law making it illegal to teach evolution in schools, specifically in science classrooms, but in schools at all. And so then immediately somebody was accused of teaching evolution, John Scopes. And it became a huge, even though it was just restricted to the state of Tennessee, it was a tremendous court battle, not only concerning whether or not John Scopes had taught evolution in his high school science classes, but also it was being played out in the court of public opinion. Is this a good law or is this a silly law? Does anyone know what the verdict of the Scopes trial was? Whether he was guilty or innocent? Yeah.
He was guilty, but he wasn't really charged for it.
That's right, very good. Yeah, he was found guilty. John Scopes was found guilty of teaching evolution, which indeed he probably did, but he was fined something like $100. Maybe that was worth a lot more money in 1925, but it was considered still a win, despite the fact that John Scopes was found guilty and fined. Sort of pro-evolution, pro-science forces considered it to be a win because of all of the publicity that the trial received, and people began to think, no, this really does make sense. This is something that we should be teaching in our classrooms. How many people have heard of the Dover trial in Pennsylvania? You guys would have been very small when the Dover trial was going on. It was played out in 2005. So in the Dover trial, now instead of it being illegal to teach evolution and charges being laid against somebody that did teach evolution, the Dover trial involved parents taking the school board to court because the school board passed a requirement that for every 4 hours you spent teaching evolution in a public science classroom, you would also have to spend equal time discussing alternative theories, specifically intelligent design. So yes, you could teach evolution, but you had to sort of set aside equal time for intelligent design on the grounds, of course, that evolution is only a theory. And so shouldn't we teach all the theories? Shouldn't we teach the controversy? That's where that terminology comes from. And the judge in that trial ruled that no, you don't need to teach intelligent design in science classrooms in public school. In fact, you shouldn't be teaching intelligent design in science classrooms. Clicker question as to why not? Why did the judge say you should not be teaching intelligent design, sort of a repurposing of creationism, the idea that there's a divine creator? Why do we not teach that in science classes? Is it because we know it's false? Is it because we know that the alternative evolution is true? Is it both of those things? Okay, let's take a look. Awesome. Yeah, the issue with intelligent design, the reason that it doesn't belong in a science classroom is that it is not a scientific idea. So intelligent design was not considered to be a scientific idea, whereas the theory of evolution is considered to be a scientific idea. And if you did the guided study assignment over the weekend, you know what makes an idea scientific or not. Just yell it out. Falsifiability, very good. Yeah, we don't consider things to be scientific unless they can be falsified. So falsifiability, my children say that people don't use the term sick beats anymore, but I don't believe that. So here's a throwback to some awesome 1980s songs. And I will start the clicker, and what I want you to do is not be ranking these songs as to which is the best song, but I want you to identify which of the statements exemplified in the title of each song, which of these is not a falsifiable statement. Has anyone heard of any of these songs? Okay, good. I don't need to update my cult refs just yet. I fully realize I'm dating myself with these songs, but they're all really good. Never Gonna Give You Up by Rick Astley. I Will Survive, of course, by Gloria Gaynor, covered by Cake. You Can't Touch This by MC Hammer, nice. Rhythm Is Gonna Get You by Gloria Estefan and Miami Sound Machine. Okay, I think most people have had a chance to click in. Which of these statements, which of these song titles is not falsifiable? Yes, nice. Yeah, most of you, or at least more than half of you, correctly identified D, Rhythm Is Gonna Get You by Miami Sound Machine, as the non-falsifiable title. So the rhythm is going to get you, I say. And maybe you say, no, the rhythm hasn't gotten me yet. I say, but it will. It will. You just haven't waited long enough. There's nothing you could do to prove to me that I'm wrong. There's nothing you could do to convince me that the rhythm might not get you at some unspecified point in the future. So that is not a falsifiable title. Okay? So Never Gonna Give You Up. That's falsifiable. What would Rick Astley have to do to falsify that title? Yeah, if he gives you up, then bang, it's falsified. Okay, so that title's fine, it's falsifiable. I Will Survive. What observation would falsify that? Yeah, you die, or Gloria Gaynor dies, or the lead singer of Cake dies. The singer will not survive. You Can't Touch This. Yeah, if MC Hammer touches this, then it's falsified. Okay, nice. Okay. So we're going to do a little bit of group work now. So I want you to get yourselves into groups of 2 or 3, maybe groups of 4 at the maximum. This idea of falsifiability is really key to how we consider scientific theories. So I want to drill down on it just a little bit more. So people on this side of the room, okay? Here's my center line. Everybody from here on down. Everyone over on this side of the room. Your job is to come up with your partner or partners with a falsifiable statement. It doesn't have to be a song title. It doesn't have to even be about science, but it has to be something that is potentially, hypothetically falsifiable. And then I also want you to come up with a potential observation that would falsify it. Okay? So that's your job. People on my right, your left. People on the other side of the room also get into small groups. Your job is to come up with a statement that cannot be falsified. So I'm going to give you a few minutes to do that. Talk amongst yourselves, write down your statements and your potential observations, and then I'll take it up in a couple minutes.
You don't actually have to know about the two trials you discussed, right?
I'm sorry?
You discussed two trials during the lecture. Do you have to know about them for the chance to exam?
You should. You don't need to know the dates or anything. You should know the basic things that they involve, like what's a scientific theory.
Well,
Yeah.
and then for like intelligent design, like you should be able to explain why it's like falsified.
Yeah,
why
everything
it's
you need
not
to know,
scientific.
the main things you need to know are covered in the outcomes. So the outcomes are listed for each lecture. So just check
Oh,
that.
all right,
Yeah.
thank you.
Okay, raise your hand. Raise your hand if your group needs another 30 seconds. Okay, most of the groups are done. Awesome. Okay, so let's start with this side of the room. Any groups want to tell me their statement?
Falsifiable statement would be that we are going to pass this course. Something that would falsify that. Don't show up for your exam.
Okay, yeah, so if you didn't hear that, falsifiable statement would be, we're going to pass this course. Yeah, hopefully that's a true statement. It certainly is falsifiable, and yeah, you would have that, the information that you need to falsify it or not at the end of December. So nice, okay. Any other, yes? All dogs are gay? Okay, yeah, I mean, it's a little bit difficult to figure out how a dog identifies, but yeah, it would be falsifiable. I guess you could observe the dog's behavior anyway. Sure, yeah. In general, or you could have said maybe all dogs are brown. but I like your I like your investigative nature. Yeah. In general, statements that start like all X are Y, yeah, those are almost always falsifiable. You just have to find a single exception to that, and that would falsify the statement. Very good. Yes, another one.
I can never be attacked by a London goose.
I could never be attacked by a London goose. Sure, yeah, saying that, such and such a thing would never happen. That is absolutely falsifiable. As soon as you are attacked by a goose in London, and it's probably going to be this spring because our geese are very aggressive, yeah, then you have falsified the statement. Okay, we have time for one more.
All birds can fly.
All birds can fly.
And then you would have to evaluate
Okay, so yeah, so here's an important point. Yeah, I like that one. All birds can fly. To falsify it, would you need to examine every single bird species necessarily? No, all you would have to do would be to find a species that can't fly. Good. Okay, so those are all falsifiable statements. What about non-falsifiable statements? Yes, in the hat over by the side. The Loch Ness Monster is real. Okay. Yeah. Why is that not falsifiable? What if I go look in Loch Ness and I look for like 6 hours and I don't see it?
Just because you don't find it doesn't like necessarily mean that it's not there.
Good. Yeah. Maybe I wasn't looking in the right place in Loch Ness. Maybe I wasn't looking hard enough. Maybe it can sometimes make itself invisible if it doesn't feel like being seen. Yeah. So basically, statements like such and such a thing exists. Those are often not falsifiable, unless you have really tight constraints. The Loch Ness Monster is in this room somewhere, and it can't turn itself invisible. One here, yes.
You will eat a delicious piece of wood.
You will eat a delicious piece of wood. Okay. Yeah, why can't you falsify that?
Because even if you have a bad piece of wood, you might have a delicious piece of wood in the future, and you can't prove that.
Okay, so maybe the first few pieces of wood you eat are not delicious, but maybe things will get better. Maybe the next one will be delicious. I would say that delicious is also pretty subjective, right? It's a matter of opinion. And in general, opinions like, biology is the best of all the sciences, that's an opinion, and those tend not to be falsifiable. Was there one up here? Yes?
We have souls.
We have souls. Okay, yeah. So such and such a thing exists. I say, well, I can't see it. I can't feel it. But the things that are, by definition, invisible and intangible and perhaps cannot be measured, then cannot be falsified. So yeah, way to go. Yeah, in the back.
When I dream in cartoons.
When I dream in cartoons. Yeah, okay, so we can't evaluate your experience for when you dream. So yeah, it's not falsifiable. And maybe you do dream in cartoons. That's awesome for you. Maybe you don't. Okay, very nice. I think that people have a good handle now on what types of statements are falsifiable and what types of statements are not falsifiable. If I said some fish can swim, is that falsifiable? Falsifiable? No. If I said all fish can swim, is that falsifiable? Yeah. Okay, good. I want to spend a few minutes now just going over what it means. When we talk about the theory of evolution, what are we talking about? In addition to being sort of socially polarizing, another weird thing about evolution, a curious thing, according to Jacques Monod, whose quote that's from, is that almost everybody thinks they understand how it works. But I want to really make sure that everybody is on the same page in this classroom and you know what are the major components of evolutionary theory. When we talk about Darwin's theory, what exactly are we talking about? It's a simple theory, simple enough that I can fit most of the major points on one slide if I use kind of small font like I've done here. Basically, when the main aspects of evolutionary theory are that life on Earth evolved, changed over time gradually, beginning with one primitive species. Maybe it was a self-replicating molecule, maybe it was something like a piece of RNA or some kind of enzyme. You'll talk more about the origins of life in winter term with Dr. Dennis. Maybe it was a self-replicating molecule, but whatever it was, it probably lived billions and billions of years ago. And that one original form of life changed over time, but more than just changing, it also diverged. It gave rise to multiple different branches, multiple different species over the course of those 3.5 billion years. And that's how we got to having millions of species on the planet now instead of just one. And what causes evolution to happen? Part of it is natural selection. Natural selection is responsible for a lot of changes in populations, but natural selection is not the only force or mechanism that can cause evolution. In cycle 6, we'll start looking at some other things that can cause evolution, like genetic drift. So natural selection is important, but it's not the sole cause of evolution. When we talk about evolutionary theory, that body of ideas collectively is what we're talking about. To go over it again with sort of a different organizational framework, Darwin, when asked to sort of summarize his theory in a nutshell, called it descent with modification from a common ancestor. So obviously this is going to be included in the theory of evolution. Yeah, sometimes evolution happens. And how do we define evolution? It's not something that occurs within the lifetime of an individual. Okay, so evolution to us, to the people in this class, to evolutionary biologists, is a change in allele frequencies that happens over time, from one generation to the next. It does not happen within a single generation. So it's different from when you level up your Pokemon and it evolves from this into that. That's not what we mean. Evolution is a change in a population. So evolution is a property of populations, and it happens over time, from one generation to the next, or over many generations, not within a single generation. Sometimes, like on the left, we can trace the evolutionary history of our own species, and sometimes that will take very long periods of time, that we can only see evolution happening if we look back over millions of years through the fossil record. Sometimes, like in the sort of classic example of industrial melanism in the peppered moths, where within a few years, the population of moths went from a predominantly light-colored form to a mostly dark-colored form. Sometimes that can happen very rapidly within a few years if the environment changes very rapidly. So sometimes we can see it happening over relatively short periods of time. Sometimes it happens very, very slowly. But sometimes evolution happens. Populations change. And this morphological change that we see, or this change in color, is associated with a change in the genotypes. Another really key component of evolutionary theory, and of course the issue that a lot of Darwin's critics had and still have with the theory, is this idea of common ancestry. Everything alive on Earth today is related to everything else. Now, some things are related more closely than other things. You are more closely related to your dog or your cat, if you have one, than you are to a bird. You're more closely related to a bird than to a fish. You're more closely related to a fish than to an oak tree. But you're related to everything alive on Earth. Okay. Later in the class, we'll talk about how to read and interpret this type of diagram that depicts the evolutionary relationships between all living things. The important take-home point here is that at some point in the evolutionary history of life on Earth, there was a single species, a single type of organism that was the ancestor to everything that's alive on the planet today. We call that individual, way back in time, the last universal common ancestor. Sometimes we abbreviate it to LUCA. So everything is related through descent from that common ancestor. Now, the flip side of that is another key idea in evolutionary thinking, and that's how new species are formed. Speciation happens. So speciation happens at each of these branching points. If you trace that tree of life sort of forwards through time, you see this branches off from that, this branches off from that, animals branch off from plants. Each of these branching points represents a speciation event, and that's how new species are formed. A single ancestral lineage diverges, it gives rise to two or more daughter lineages. That's how we get from one species at the bottom of the graph to millions and millions and millions on the planet today. Another important point is that most evolution Evolution is what we call variational. It requires variation in the population in order for evolution to happen. Yeah, questions on that? You good? Okay. On the top here, we have what's known as a transformational view of evolution. Okay, so we have a population with no variation starting on the left hand, and the environment is changing every single individual in that population. In this case, it's making them more stretched out and more orange. And then each of those individuals is passing on those acquired changes that they've gotten to their offspring. In the reading, who did you read about that would have agreed with that view of evolution? Remember? Yeah. Lamarck, very good. Yes, this cartoon on the top represents Lamarck's view of evolution, what we can think of as a transformational view of evolution. One of Darwin's big contributions was recognizing the importance of variation, genetic variation. Darwin pointed out evolution will only happen if we start with a population where not every individual is the same. Individuals differ in their phenotypes and their genotypes. And in this particular cartoon, individuals that are sort of elongated and dark blue are more successful than individuals that are little white circles. Okay, so it's not that individuals are changing over the course of their life. You don't need that to happen. All you need is for there to be variation in the population, and some variants are more successful than others. And through that process, just because the longer and the bluer you are in this cartoon, the more successful you are, over time the population changes. But it's because of variation. It's not because the environment is changing the phenotype of individuals. So evolution is variational. Most evolution, we think, is gradual. That is, you don't typically see large evolutionary jumps. Instead, it could take many, many generations to see a large evolutionary change. So when we say, for example, that modern birds are descendants from Archaeopteryx and other dinosaurs, that we're not saying that, at some point an Archaeopteryx laid a bunch of eggs and from some of those eggs hatched baby birds. Instead, that would have taken place over, in fact, millions of years, many generations. And if the fossil record is good enough, as indeed it is, you can see evidence for so-called transitional forms, things that are descendants that are sort of intermediate between, in this case, an Archaeopteryx and a modern-day bird. Gradualism and transitional forms. And finally, selection is important. Many people think of Darwin as being sort of synonymous with natural selection because that was a huge contribution of his. Selection is one of the many components of evolutionary theory. So selection results in what we call adaptation. Adaptation being a trait that makes an individual better suited to its environment. So these deep-sea anglerfish, for example, have many adaptations that make them well-suited to living in the deep seas in very dark environments. They've got these phosphorescent bacteria that help them lure prey items in by sort of glowing in the dark. And selection is important, but it's not the only reason that populations can evolve. So adaptations occur because of selection, but there's other things that can cause evolution other than selection and adaptation. And while the deep-sea anglerfish is quite well suited to its environment, and most living things are pretty well suited to their environments, not everything is perfectly suited to their environments, okay? And so even though selection is a powerful force, there are limits to what it can accomplish. Every adaptation has limits. Here you see a poor little snowshoe hare that has turned white, perhaps too early in the winter before the snow is sticking on the ground. And so it's no longer cryptic, it's no longer well camouflaged to its environment. And this is happening to many populations due to the changing phenology of the seasons associated with climate change. So what are some reasons that populations might not be perfectly suited to their environment? First of all, environments can change over time. So if winter is coming later and later, or spring is coming earlier and earlier every year, then it may take a population, it may take them a long time to evolve in response to that. Sometimes evolution is fairly slow relative to how fast the external environment can change. Are there any other things that can sort of put limits on, why, and any other reasons you can think of for why a population might not be really well suited to its environment? Yeah.
Time between generations.
Yeah, the time between generations. So again, yeah, the environment can change over time, and there's sort of a lag. And if the environment changes, then maybe the environment to which you are adapted is different, and so then your offspring might not be well adapted to that environment. Yeah. Yes.
Every step during the evolution must have a viable niche to itself.
Yeah. So evolution happens gradually, and in order to be favored, everything has to be an improvement over the previous version. Yes. Predators. Yeah. Okay. So that's a good point. So you may be adapting in response to your environment, but you also have like natural enemies, parasites and predators, and they may be adapting to become better and better and better able to capture you or infect you. And so we'll talk more about evolutionary arms races later in the course, but that's a great point. Another thing is that selection can only favor mutations after those mutations have occurred. Okay, selection can't cause a new helpful mutation to happen just because it would be helpful. This is why things like viruses, things like retroviruses, things with very, very, very high mutation rates have a huge evolutionary advantage over us, because they have so much genetic variation because their polymerases make so many mistakes. Selection can only favor a new allele after that new allele has occurred. And finally, there's often compromises between competing demands. Okay, so for you guys in your life, any time you spend studying chemistry is time that you don't have available for biology or for sleeping or for socializing. So you only have so many hours in the day. Organisms only have so much energy that they can take in, and they need to divide that. They need to allocate that to their immune system, or growing, or reproducing. Another example of a compromise between competing demands is if this guy's a male peacock and he grows a big long tail, then that makes him very attractive to female peacocks, which is good, but that comes at a cost, and the cost is that it makes him very conspicuous to predators. Okay, so competing demands, it's important to be sexy, but it's also important to be alive. How do we balance those? For all these reasons, not everything is perfect. Not everything is perfectly suited to its environment. So what I want to do in the last few minutes of the class is to get back in your same little small groups, your groups of 2 or 3, and you have in your notes a list of, I think, 8 observations or hypothetical observations. You just have to choose one of them. Each group choose one. And think about all of the aspects of evolutionary theory that I've just talked about. Which one or 2 of those is it most relevant to? And specifically, how is it relevant? Does it alter your thinking about that? Would it falsify one of the principles of evolutionary theory? So take a few minutes to go over that, to do that, and then we'll take them up in a couple minutes. Go. Okay, great. Let's go through a few examples. Yeah. Did anyone talk about the first one? Coelacanth fish have hardly changed at all, but HIV can change really fast. Or any thoughts as to which of the tenets of evolutionary thinking that relates to? Yes. Yeah, so it brings into, so it sort of relates to multiple sort of tenets of evolutionary theory. Nice, and your explanation is bang on. Yeah, things evolve, but we don't necessarily see natural selection happening if there's not variation in the population, or if some variants are not more favored than others. For whatever reason, the coelacanths have not been evolving, but HIV has been evolving in response to selection pressure that we put on it. It also, I think, would have tiebacks to the idea of gradualism as well. Some people might interpret rapid emergence of antiviral strains, of antiviral resistant strains as, oh, gradualism doesn't work. That's sort of nonsense, because a few months is, a very short time for us, but it's actually enough time for many, many, many generations of virus. So it is relevant to gradualism, but I would say that observation does not disprove gradualism. Nice. Anybody do the whale and dolphin embryos and the hind limb buds? That evidence of, yeah.
There was evidence that the environment changed over time, so while these things might have been useful to a previous environment, it's no longer currently useful to the organism.
Yeah, so it provides evidence, first of all, that species change over time. Whales and dolphins don't need hind limbs anymore, and so the adult whales and dolphins don't have those. Is also good evidence for common ancestry. Okay, so why do the embryos have those hind limb buds? Probably because they evolved from an ancestral species that did have fully functional hind limbs. Okay, so many of these actually touch on a couple different aspects of evolutionary theory. This example, of course, involves the nature of selection and how there can be trade-offs, in this case, between your mating success, how sexy you are, and your survivorship, and how you may not be able to have it all at once, how adaptations are not necessarily perfect. Anyone do this one about the genetic code? What is that evidence of? Yeah. Common ancestry, very good. Yeah, almost everything has the same genetic code. There's a few species that have a slightly different genetic code, but it's almost the same as the one that we have. And the best explanation for that, the simplest explanation for that, is that everything on Earth has evolved from descent from a common ancestor. So I won't be able to go through all of these, but feel free to play around with the other examples that we didn't go through today. Post questions on OWL if you have them. Come to my office hours if you have questions. And the rest of you, I will see you in cycle 6.